Oh, hello there. I was just enjoying some light reading, but it's very kind of you to join me. I was just about to embark on a journey beyond sight and sound, where fact meets fiction. Come with me into the imaginary zone. As we get into studying imaginary numbers, your first question might be, why? We have our regular real numbers, and they're enough to deal with stuff. I mean, even negative numbers are a little bit goofy. Why do we need this whole other kind of number to deal with things? And the reality is that you may not use imaginary numbers in your everyday life, but mathematicians in the 1500s were looking at how to solve different polynomial equations, and they realized that sometimes it was useful to work with the square roots of negative numbers. And over time, it became to realize that these square roots of negatives applied to things like trigonometry. And even later, in the 1900s, they showed up in quantum mechanics as a necessary part of how the world functions. So even though imaginary numbers are a weird concept that are hard to conceptualize and don't have day-to-day practical impacts on the average person, they are something that is important to how our world functions and how mathematicians and scientists look at it. So that's why we study them. The basic imaginary number is I. It's a lowercase I. In some fields, like electrical engineering, they use J instead of I for reasons that make sense when you're in that field, just so you know. But mostly it's written as I. And I is defined to be the square root of -1. Now, for years, you've just been told you can't take the square root of negative because nothing times itself gets you a negative, which is true as long as you're considering real numbers, but imaginary numbers times themselves do get you a negative. So I is defined to be the square root of -1, and that is the basic imaginary number. So any number that has the square root of a negative winds up having an I in it. For example, if we wanted to figure out what is the square root of -4, well, we learned when we were dealing with roots that if you have the square root of something, you can say that that's the square root of two numbers that multiply together to get you that. So the square root of -4 you could rewrite as the square root of -1 times the square root of 4. And we know the square root of -1, well, I've just said the square root of -1 is I. The square root of 4 is a simple thing that we can calculate. The square root of 4 is 2, so the square root of -4 is 2I. Likewise, for any perfect square, if you have the square root of -16, well, the square root of 16 is 4. The square root of -1 is I, so root 16 would be 4I. You can also figure out imaginary answers for square roots that you need to break down to simplify. For example, you can take the square root of -20. Well, 20 is 5 times 4. 4 is a perfect square. So 20 is equal to 2 root 5, but then there's also a -1 in there. The -1 becomes I, so we've got 2I root 5. So you notice that root 20 would be 2 root 5. With the negative, you just throw in an I there. So if you're simplifying a negative radical, you do it just the same way you would a positive radical and throw in an I. For example, if we had square root of -108, then we just break down 108. 108, what is that? That's 9. We could do 9 times 12. And then 12 is 3 times 4. So square root 9. And then we got the -1, so that could be a square root 9 times square root 3 times square root 4 times square root -1. Root 9 is 3, root 4 is 2, 3 times 2 is 6. root negative 1 is I, and root 3 is just root 3. So negative root 108 simplifies to 6I radical 3. So any radical of a negative you can simplify just like you would the radical of a positive, but with an additional I pulled out of it. Powers of I are interesting to look at because they do, well, something kind of interesting. So we know I is the square root of negative 1. We also know from before that if you take something like root 2 times root 2, that just cancels out the radical and gets you 2. Root 5 times root 5 is just 5. So if we take I squared, that's going to be root of negative 1 times root of negative 1. That's just equal to negative 1. So I squared is negative 1. If we keep going, we take I cubed. Well, that's going to be I squared times I, to add a third power. So that's just negative 1 times I, or just negative I. Again, if we keep going, I to the fourth, well, you multiply another I, that's negative I times I, which is negative I squared. I squared is negative 1, so that's negative 1, which is just 1. And if we multiply another power of I, we have 1 times I, which is just I. So you can see we've cycled around. If I write this out a little more cleanly, without all the stuff in between, obviously I is just I. Then I squared is negative 1. I cubed is negative I to the fourth is 1, and then the cycle repeats. We could also go the other direction and say I to the 0 is 1. Any number to the 0 power is 1. So you can see this pattern repeats every 4 powers of I. Since it repeats every 4 powers of I, we can figure out bigger powers of I. So if we look at I to the 0 is 1, we look at 0 through 3, we've got 1, I, negative 1, negative I. Right? And then it repeats. 1, I, then I to the 6th would be negative 1, I to the 7th would be negative I. So all we need to know to evaluate a larger power of I is the remainder when we divide the power by 4. For example, if we take I to the 8th, well, that's just another cycle, 6, 7, 8. If we count it down, we figure out, well, I to the 8th is going to be, if we take 8 divided by 4, we get 2 with a remainder of 0. So that means that I to the 8th is going to be the same thing as I to the 0. Therefore, I to the 8th is equal to 1. We could go bigger if we take I to the 30th. We can take 30 divided by 4. And 4 goes into 30 7 times. 7 times 4 is 28. So there's a remainder of 2. And since there's a remainder of 2, that means I to the 30th is the same thing as I squared, which is just negative 1. I to the 71st. We can figure out 71 divided by 4 is 1. Subtract, we get 3, drop down the 1, 4 goes into 31 7 times, that's 28. 3, so there's 17 with a remainder of 3. The remainder is 3, so I to the 71st is the same thing as I to the 3rd, which is just negative I. So we can figure out those larger powers of I just by looking at what the remainder is and equating that to one of these first 4 values, because the powers of I cycle every 4 powers. Complex numbers are closely related to imaginary numbers. Complex numbers are just numbers that include a real part and an imaginary part. So real numbers are all the regular numbers, 2 and root 7 and 1.3 and negative 3,000. Those are all real numbers, or negative 2.387491. So complex numbers are numbers that have a real part and an imaginary part. So they have a regular real number, and then that's combined with something that has an I in it. So 2 minus 3i is a complex number. Root 5 minus 2i root 3 is a complex number. 1.261 minus 0.147i is a complex number, or 7 minus 35 pi I is a complex number. These are all written in standard form for complex numbers. Just so you know, standard form of a complex number looks like this, where you put the real part first and the imaginary part second. You'll see things where the imaginary part is first. It's still a complex number. It's just not written in standard form, and you'd have to change it if you wanted to write it in standard form. Yeah, and there's a little bit of notation. If you have an imaginary number, say we take this 2 minus 3i, z is often used to represent complex numbers. I'm not really sure why, but if you have 2 minus 3i, there's this notation that says real, re, of z. And this means the real part of the number z. Well, the real part is just the part that doesn't have an I attached. So the real part is 2. And then the other part of it, the imaginary part of z, is just the imaginary part. So it's whatever's attached to the I. It doesn't include the I itself. You just list the coefficient on the I, the number that's connected to it. Yeah, and numbers, now that we are learning about I, numbers can either be real, imaginary, or complex. So if it's one thing that has an I attached to it, if it was just negative 3i or just 2i root 3, that would be imaginary. If it was just 1.261, that's real. Any combination that has one term that's real and one term that has an I is complex. You have real, imaginary, and complex numbers that we are working with now. Thank you for joining me on this journey today. It's been quite a ride. I hope I haven't changed things too much for you, now that you can see beyond into the realm of the imaginary. I hope I haven't made your lives too complex. Keep it real.